Hello, this is Lab 3 vibration, beam vibration. My name is Rohit Gupta. The outline of this, of course, is the laboratory objectives, experimental setups, experimental results, conclusions, and references. The objective of this lab was to analyze the vibration of a cantilever beam instrumented with the strain gauge, to use a strain gauge to measure dynamic tip displacement of the beam, and to perform spectrum analysis of tip displacement to find the natural frequencies of the beam. Experimental setup, as you can see here, starts with my laptop connected to the MSP via the USB connection. The MSP is then connected to the Wheatstone bridge, which as you can see there in the picture. The Wheatstone bridge is then connected to the strain gauge, which is glued to the top of our ruler, which is acting as our cantilever beam. It is fixed with a C-clamp. The setup is like I just said. For static measurements for the strain gauge sensitivity, as you can see here, here's the data with the line of best fit. The sensitivity was 0.1 millimeters per volts. Purpose of this task was to determine the strain gauge sensitivity by analyzing the relationship between its voltage output and beam tip displacement. The beam was loaded at its tip and corresponding displacements and voltage readings were recorded from multiple trials. The results showed a linear relationship where voltage increased proportionally with displacement. Sensitivity, calculated as the slope of linear regression, was found to be 0.1 millimeters per volts, like I said. This confirms proper calibration, and everything else that could be wrong with this is because of equipment failure. As you can see here in the static measurements for beam equivalent stiffness, the data was very linear and almost exactly perfect. The assumptions for this experiment were that the beam remains within this elastic limit. The material properties are uniform along the beam, and the beam is simply supported and follows linear elastic behavior. The goal of this task was to analyze the static behavior of the beam by studying the relationship between the applied load and the tip displacement. The beam exhibits linear elastic behavior as shown by the linear relationship. And the stiffness was calculated by calculating the slope of the load versus the displacement. For the dynamic measurements for the initial displacement excitation, the initial displacement was implemented by displacing the beam tip downward by 20 millimeters. With my finger, I slid away from the beam, allowing it to oscillate. The displacement quickly goes to zero over time because the ruler wants to return to its resting position, as you can see here in the data. The steady state peak is around negative 75 decibels. These are some of the equations that we use to get the estimation for these natural frequencies and damping ratios. It was determined that the system is underdamped. This is a comparison of the experimental versus the theoretical responses. As you can see, our experimental results were very incorrect in this situation, although our analytical results are absolutely correct. This is the equation on the left side that you would use to calculate that. And this is for case 2 with the impulse excitation. It was implemented by dropping a weight at the tip of the beam, and the weight in our case was a coin. It was a nickel of 5 grams. This displacement starts out very wonky, but then quickly settles out, as you can see here in the plot. For the vibration treatment description in the different cases, the only difference in the two cases was that the vibration dampener was first of 1 layer of duct tape, and the second was of 5 layers of duct tape. Of course, the second case yielded better damping results, of course. And here's the results physically. And this is the summary with all the cases and the natural frequencies. The first natural frequency was the same across all cases, suggesting that the beam vibrations do not change with different test conditions. The values of the damping ratio being close to 0 or negative is very odd, suggesting that the issues occurred during data processing. The damped natural frequency, however, remained the same as the first natural frequencies for cases 1, 2, 3, which align with that theory. But in case 4, there seemed to have been some issue with data collection. And to conclude the PowerPoint, strain gauge sensitivity was within our expected limits, indicating linear results. For the beam equivalent stiffness, the beam has linear elastic behavior based on the plot that align with our values from the theory. And the vibration control yielded a thicker tape yielded a better damping property for vibration control. And for dynamic measurements, different test conditions did not change the first natural frequency, and damped natural frequency remained the same as well. Here are my references. Boom.